Okay, let's begin. So we are still in chapter 4, determinants. And last time, we figured out how to find the determinant and what it means. And last time, we also looked at what we call pivotal condensation.
Professor, what is that? I did not understand. Can you talk, give an example?
I did an example.
I
This is using row operations. To make computing determinants easier. Right, so we know that based on how we define a determinant, it's easiest to compute one if you expand along a row or column that has the most zeros, but there might be situations where you don't have any zeros, but you can actually create them with row operations. And so when you do that, create a bunch of zeros with row operations in order to make computing the determinant easier, that's called pivotal condensation. And you just have to be careful with the row operations that you're using. If you use a type 3, it won't change the determinant at all, so you don't have to make any adjustments. But if you use a type 1 or 2, there are adjustments to make. In particular, if you try to create a lot of zeros in a row or a column by ended up swapping 2 rows at some point, you have to negate the determinant each time you swap 2 rows. And if you multiply a row by some non-zero constant, you'll have to divide the determinant that you obtain by that non-zero constant. So there are adjustments to be made for the first 2 kinds of operations, but a type 3 will make no difference. You can do any amount of type 3s you want and it won't change.
Professor?
Yes?
Well, it is not mandatory to do by pivotal condensation, right? You could do it in a regular way.
It makes it easier. Of course, that means you could do it otherwise. But if you don't want to make a mistake, you want your life to be easier, you use pivotal condensation. So now we will look at some more determinant theorems. And this will help you with, well, for one, some of the bonus problems that I asked you about determinants on the test on Tuesday. So the following are true. So there's a theorem. Not going to prove them, just going to state them, and you can know that you can use them every now and then. This one is kind of directly related to how type 2 operations affect the determinant. So given if you know the determinant of a matrix, then what would you get if you take the determinant of a scalar times that matrix?
You would get
K not equals 0 is a scalar.
So wouldn't it be K det A?
No.
A negative something?
No.
Like that?
What did the rule that we said? If we multiplied a row by a constant, that multiplied the determinant by a constant, right? What does it mean to multiply a matrix by a constant? You would multiply every row by k. So if I know each time I multiply a row by k, I have to multiply the determinant by k. What would happen if I multiply the entire matrix by k?
K cubed.
Or is it 2?
K to the n.
K to the n times the determinant. Where k is a scalar and n equals the number of rows of A. there's another theorem. This basically tells us that the determinant of a product of matrices, provided the determinant of each exists, is actually the determinant of the first one times the determinant of the second one. Determinants actually distribute across products. They don't distribute across sums, so I don't think you can actually do that, but they do distribute across products. In fact, this kind of tells you that what would that mean? So this is representing A multiplied by itself K times A times A times A, K times. What would the determinant of such a thing be?
Determinant of n to the power of k.
I would take the determinant of the original matrix and I raise that to the power of K. Because this would just, if I take the determinant of this, it's just the determinant of that times the determinant of that times the determinant of that, that will end up multiplying the determinant by K times, and so we can have this happening. Right, so this is just a direct consequence of that being true. Determinants do not distribute across sums, so I'm not giving you that rule because it's not a thing. But it distributes across products. Other rules did I tell you? So that's true. I mean, we haven't done inverses yet, but when I talk about inverses and you understand what it is, this will make sense. The determinant of A inverse would be 1 over the determinant of A. A inverse equals, this is A inverse. We'll talk about this in chapter 5, so, and you'll understand what this means when we get to chapter 5. Another theorem. I think I mentioned this before, but the determinant of A is exactly the same as the determinant of A transpose. If you switch all the rows into columns, it actually won't make any difference. You'll get exactly the same numbers if you, instead of expanding along a row, if you expand along the column in the transpose, you'll get exactly the same numbers in exactly the same order. Nothing will be different. So with that being said, we can do an example, which is pretty much like the example that was in the test. So let's say given that A is, let's make it a 3 by 3 with, and let's say you did all the work to find the determinant of A and you found that the determinant of A is -2, and I ask you to find what is the determinant of 2 times A cubed times A transpose times A inverse. Now what you do not want to do is to compute each of these individually, then multiply each of those,
That's what
and
I did.
then you find the determinant, because that would...
That's what I did in
I almost did
exam.
that.
Not that that's wrong, but that is not very efficient.
You should have told
But
us
these
last
theorems-
week.
It's not a real bonus if I tell you how to do it before I ask. So with these theorems, that's actually not that bad. If I know the determinant of the original, give me the determinant of any product of variations on the original and I can find it. So the idea is here, the determinant of this thing of 2A cubed A transpose A inverse is going to be equal to, first of all, what do I do with the 2 according to the theorem? I would take it to 2 to the power 3, and that's going to be multiplying by this guy. It's going to be the determinant of A, and I'm going to cube it. this guy, determinant of A transpose, is, let me write it out a little bit more. So this is going to be 2 times the determinant of A cubed times the determinant of A transpose times the determinant of A inverse. This is going to be 2 cubed times, now this one is the determinant of A cubed. This one is exactly the same as the determinant of A. And this one is just 1 over the determinant of A. You might be worried about, well, what if the determinant of A was 0? In this case, we know it's not 0, so that's not an issue. But in the next chapter, I'll show you that if A inverse exists, it means the determinant of A is not 0. So you never have to worry about something like that happening.
Professor,
Yes.
how do you get a 2 to the cube from it? Is it by 3 by 3 matrix?
The theorem that I wrote down here, where I told you the determinant of K times a matrix is K to the n times the determinant of a matrix.
Yeah.
So in this case, the K is 2.
K is 2.
The number of rows is 3, because I know A is a 3 by 3.
Okay.
And so I raised 2 cubed. And so finally the answer is going to be, now these are just numbers, so the rest of it is arithmetic. That's 2 cubed times 2 cubed times 2 times 1 over 2. And that would of course cancel, so that's 2 to the 6. Which I believe is 64.
Wait, is it not negative too?
Yeah,
Is it
negative.
Determinant
Was
of
it negative?
They are negative.
Negative.
Yeah.
Okay, so this here, negative 2.
No.
Oh, no, that's fine. This is
No, that's fine. Yeah. That
This
one.
is negative 2.
This was negative.
This is negative 2 times negative 2.
Negative.
And so the negatives cancel here, but we'll leave with this negative here, so it's negative 2. Yeah. And one more thing I want to tell you about determinants. And state Cramers rule in general. So, given a system of equations AX equals B, define the following. Define D to be the determinant of the coefficient matrix. And define D sub xi to be the determinant of AXI where AXI just means the matrix A with the ith column replaced IB. I'll write down an example of what this would look like. So we're defining these terms. Now here's what Cramer's rule tells us. Which you might have seen it before, but I'm going to state it more generally. And in practice, you'll apply this for like a 3 by 3. You can do this for any size, any square system. So given a square system, that means that, of course, if you're talking about determinants, it has to be a square matrix. So you can put in square here. Make these two definitions. I'll show you what that looks like in a little bit. Then, it turns out we can find the solution to the system in terms of determinants. If D is not equal to 0, the system will have a unique solution. There will only be one vector that solves this system, given by xi equals dxi divided by d. So that means, i.e., your x1 would be the dx1 over d, your x2 would be the dx2 over d, etc. Where d is just the determinant of the coefficient matrix, dxi is the determinant of the matrix you get if you replace the ith column of A with x, with b. If d is 0, there are two cases. One, if all the dxi equals 0, there are an infinite number of solutions. And two, if any of the dxi are not 0, the system is inconsistent. So Cramers' rule covers all the possible cases that we know about systems. In the case of the determinant of the coefficient matrix is not 0, you will be able to find a unique solution to the system. And we actually have a formula for how to actually compute that. And if your determinant of the coefficient matrix is 0, there are two possibilities. You'll either have infinite solutions or it'll be inconsistent. And you know it'll have infinite solutions if all the other determinants are also 0. But if any one of them is non-zero, then the system is actually inconsistent. So let's look at an example. So I'm going to say use Cramers' rule to solve for x. If x minus 2y plus 3z equals 1, 2x minus y minus z equals 0, minus 3x plus y plus 4 equals 0. So that's a possible question on an exam. And of course, if the problem says use Cramers' rule, then you won't get credit for any other method. You have to use Cramers' rule.
the answers are not involved in the determinant, right?
What do you mean the answers?
How 1, 0, 0 are the answers if we write it as an augmented matrix?
Well,
they're like the right side of the equation.
in
It's not
this
involved
case-
in the determinant, right?
Yes, it is.
It is.
In some of them. So let's actually see what Cramers rule says. So what is A here? And if I think of this as AX equals B, A would be what?
1, negative 2, 3, 2, negative 1.
Minus 3, 1, 4.
4.
Right? What is the X vector? Or is this X, Y, Z? Right? So that guy is like your X1, X2, X3. And then your B would be the constant vector, 1, 0, 0. Now, according to the definitions in Cramer's rule, what we have is that B would be the determinant of A.
Wouldn't for B it would be negative 1, 0, 0?
Huh?
Wouldn't for B it would be negative 1, 0, 0?
For B?
There's one.
No, it's 1.
You leave it on the other side.
No, this is in the form AX equals B. Right, B is the guy on the other side. So B is just this matrix over here, 1, 0, 0. A is the coefficient matrix of that, and the variables tells you what's the components of your solution. Okay? So your D would be the determinant of this, which I believe we already found. That was 4 in previous class. And so now what you can do is you can find D sub each of the vectors. In this case, I care about D sub X because I want to solve for the X. So what that means is I'm going to take the determinant of this guy, except the X column is replaced by D. So I'm going to put 1, 0, 0. And I'm going to find the determinant of that. Yes?
How'd you get the 4?
We found the determinant last time. We did. It was a pre. But you would get it if you were doing this. You would have to expand along a row or column, and you'll ultimately get that. I didn't want to take the time to do it again. Right? So D is the determinant of this using Laplacian expansion. If you want, you can use pivotal condensation to help you, but ultimately you'll get to the answer 4. Once you do that, since we want to solve for X, we need to find D sub X. What that means is you're going to take the X column and replace it with the B column in the original determinant.
Professor,
Yes?
so like in this case you have something called the X column. If you want to solve for the Y column,
You would replace the Y column with the B column.
with the B column, right?
Yeah.
Okay.
And then you find the determinant. If you wanted to solve for Z, you would replace the Z column with the B column, right? But once you replace the appropriate column for the variable you care about, you find the determinant of that. Now, in this case, this is not going to be so bad. We can actually do this. This is, remember, it's a plus sign here. I'd expand along the first column because it's like 1, 0, 0. So that would just give us minus 4 plus 1. Right? Agreed? Okay, and so,
And then you need to divide it, right?
and then you need to divide it. So this
So
would mean
dx over d.
that dx divided by d, your x would be equal to dx divided by d, which is going to be minus 3 over 4. And by the way, you can look at the 2x2 example that I gave you when I was originally talking about the determinant, I said, pretend we have this 2x2 system, a x plus b, y equals this, and cx plus dy equals f. And I wrote the solution as a ratio of a couple things, where I said the denominator was the determinant. If you look at the top, you'll notice at the top of that, if you look at it back in your notes, the top of that was actually the determinant of if I replace the x column with the answer, the constant matrix. So this works in general for any square system, but that's how you do it. And you can solve for one variables individually. It's Cramer's rule. So there's very typically a problem like this on the exams, and it will be on test 4, and more than likely it will be on your final as well. Right, so they'll give you a system. It's going to usually be a 3x3. I've never seen them ask a question like this for anything larger. I've also never seen them ask it for a 2x2. So you can expect a 3x3, and they'll say solve for one of the variables only using Cramer's rule. Don't solve for the other two, and that basically means you're going to find D, find D with whatever respect to whatever variable they ask you, and you take the division. Right? And as long as your D is non-zero, you will be able to find the solution. Yeah, that's basically it. Nothing else to say there. And I think that wraps up chapter 4. So now we're going on to chapter 5, where we're going to talk about inverses. Also something I asked you about on the bonus, so now we're going to cover inverses.
Professor,
Yes.
when we expand, do we have to use that column that we replaced? Or we can use that?
You could use any column. It's finding a determinant. You find a determinant of however you want to do it. You'll get the same answer no matter which column or row you expand. Okay, so let's see what do I want to tell you about determinants. Let's start with the definition.
Like we choose X in place, but then after that, we just determine.
What? What happened?
Just reiterating.
Yeah, there's no reason that we have to expand along that column that we replaced. We can expand along any row or any column in general. If we're finding determinant, we have the freedom to choose. Okay, so definition. Let A be a square matrix if there exists a matrix B such that, and let this be n by n, such that if I take A times B, I get the n by n identity, and it works in the opposite order as well. B times A, I get the identity. Then we say A is invertible. And its inverse is B. In this case, we denote B equals A inverse. This is red, A inverse. And it's notation, right? This is notation. If I say A to the minus 1, it does not mean 1 over A, right? It's kind of like sine inverse, how sine inverse doesn't mean 1 over sine. Because, in fact, in the land of matrices, remember, there is no such thing as division. So nothing will ever mean something like this, right? Because division doesn't even exist. So it's just a notation. When you write a matrix to a -1, it just means you're referring to the inverse of the matrix, which means it is a matrix that if you multiply the original matrix by, you get the identity. i.e., if you take A times A inverse, you get the identity. And if you take A inverse times A, you get the identity. A useful fact: if one of the above work, the other will as well. So you only need to check one of these equations if you're checking something. So if you have a matrix and someone gives you another matrix and claims that this is the inverse, you can actually check it pretty easily. Just do the matrix multiplication. As long as the result is the identity, that's the inverse. Technically, we define it in terms of it should be able to go in either order, but you can actually prove that if this is true, then that will be true, and if this is true, then that will be true. So you really only have to check one of them. So that cuts down on the calculations that you have to do. But if you're given something that you suspect is an inverse, you can check it by checking this equation. And I'm going to ask you to find the inverse sometime. So if you find the inverse and you want to check that you didn't make a mistake, you can check it by checking either one of these equations. So that's what an inverse is. So it's a matrix that when I multiply, I get the identity.
Professor,
Yes.
I have a question. So A times A inverse would be identity. You means the real matrix or?
The real matrix? What do you mean?
So, what do you mean the identity matrix? Like,
This is the guy with ones on the main diagonal
oh,
and
okay.
zeros and ones. It's a diagonal matrix where all the diagonal entries are one.
Okay.
Right. That was the identity matrix. That's the same matrix that if you multiply it by any other matrix, it just gives you the matrix back. Okay, so we have that definition. Another vocabulary word. You'll see it all over the place. So let me just say that. If A is invertible, it is called, let's put the chalk today, non-singular. If A is not invertible. It is called singular. Chop must be freaking out about the weather. On Sunday was like what, 40 degrees? How is it 90 degrees today?
Everything.
How?
We skip spring.
We skipped spring. We started straight from winter to summer, 0 to 100. Here's a theorem, a statement you will just take on faith because we don't really prove anything in this course. It turns out that A is invertible if and only if. That means it goes in both ways. The determinant of A is not 0. Meaning, if you know there's an inverse matrix for the thing, it means the determinant of the original is not 0. If you know the determinant of the original is not 0, an inverse exists somewhere. i.e., if the determinant of A is not 0, then I know I can find a matrix B that fit the previous definition. Then A inverse exists. And if we know A inverse exists, then that must mean the determinant of A is not 0. I know the determinant has to be non-zero. Which now, Cramer's rule makes sense when you think about it with the other theorem I told you about, with the solutions to a solution to a system of equations, right? We know that Cramer's rule says that the determinant of the coefficient matrix is not 0, there's a unique solution, and here we can kind of see that, oh, that means that this actually works out, and ultimately we're going to see that that means there's a unique solution. I'm going to tell you how to find inverses, but I'm just telling you about some important things for now. So inverses are useful in a lot of ways in general, but why do we care? If you're given a system, AX equals B, and we know A inverse exists, then basically what that means is I have a shortcut for finding the solution to that system. X equals A inverse times B is the only solution. So that's one reason why we care. It helps us solve systems of equations. Why? Well, if you're given AX equals B, what you can do is you can just multiply both sides by A inverse. Right? Multiply both sides by A inverse on the left. Matrix multiplication is not commutative, so the order in which you multiply matters. I multiply by on the left here, so I have to multiply on the left on the right side. But if I multiply A inverse times A, that just gives you the identity. And the identity times X, well, that's just X. And so you end up with X has to be A inverse times B, assuming the inverse exists. And that will be the only solution. So that's why we care about finding inverses. So now the question is, how do we find inverses? Two methods. One we have all the tools for already, the other one I'll have to give you some extra definition. We look at two methods. One is going to be called the row reduction method. Two, it's going to call the adjoint method. So if you have a square matrix and its inverse exists, it's a very useful thing. In particular, it helps us to solve systems just using a matrix multiplication. So finding the inverse is going to be something that's important, especially for this class. And how do you find it? There are two main methods. One is using row reduction, which we already know how to do. And the second is using the adjoint method, which I'm going to tell you about how we do that. So let me describe each method. One. Here's how we're going to do it. So step one is to augment the system. Augment the matrix. By the way, it's useful to know the left side will be IN. It has to reduce the identity matrix on the left side. If it doesn't, it means either it's not invertible or you made a mistake.
That's Gaussian elimination, right?
Huh?
That'll be Gaussian elimination, right?
Yeah, well, Gauss-Jordan elimination, technically you're going all the way to the reduced row echelon form. Here you don't have a choice. You can't stop at row echelon. You have to go all the way to reduced row echelon. That's very important. So that is, if you start with A on the left, augmented with the identity, and then you do a bunch of row operations to find the reduced row echelon form. The reduced row echelon form will always have this form. The identity will end up on the left side, and the guy that you have on the right side of the bar will be the identity. If you do everything correctly and this doesn't happen, it means there is no inverse. But as long as there is an inverse, and you'll have reason to believe that there is, because I like tell you and ask you to find it, then this process, you can use it to get to the inverse. It's the row, we literally just do row reduction. Find the reduced row echelon form. So with the matrix on the left, the identity on the right, find the reduced row echelon form of that. The identity should end up on the other side, and the inverse is going to be the guy that's on the right side. So now I will show you there's a 2x2 example here. Did I do a 2x2? I did do a 3x3. Let's do the 2x2 first, and I'll go through it, and then we'll do the 3x3. Example. Find the inverse of 1, 2, 3, 4. By the way, 1, I know the inverse would exist because the determinant of this is 4 minus 6, right? Which is minus 2. It's not 0. So I know the determinant actually exists. I'm going to ask you to find it. Here's one method. I'm going to use this method. Right? There's going to be another method. And in fact, there's a nice shortcut formula for 2x2 matrices, but that formula actually comes from the other method, from the second method, from the adjoint method. That's where that formula comes from. But let's do the row reduction method. So what I'm going to do is to, using 1, I'm going to put 1, 2, 3, 4 right beside the identity. find the reduced row echelon form. So I know my pivot is going to be here, so I'm going to leave that alone. Immediately, I want to make this 3 into a 0. So how can I do that?
Multiply R2 minus 3R1.
Row 2 minus 3 row 1 would work. 3 minus 3, 0. This minus 6, minus 2. This minus 3, minus 3. This 1 minus 3 times 0 is 0. This is 1. Now what?
Make that 2 as 1, correct?
Not so fast. You're going to get a fraction here. Remember, to avoid mistakes, you want to leave fractions till the very last. I know I'd be able to make that into a pivot by dividing by minus 2, but I'd hold off on that. So I know that the second pivot is going to end up here. I know I can get it, but I'll just wait. I'll come back for you.
So you will make everything 0.
So now I know the pivot is going to end up here. To find the reduced row echelon form, it means I need this to be a 0. And that's actually, I can just add them right away.
Yeah.
Right? So I can replace the first row by just adding row 1 plus row 2. 1 plus 0, 1. This plus that, 0. This plus that, minus 2. This plus that, 1. And so now that's actually going to be in a nice form. Now I can take the row 2 and divide by minus 2. So this would be 0, 1. This would be 3 over 2. This would be minus 1/2. And that's the answer. It was a 2 by 2. It's not going to take a very long time to find the answer. Minus 2, 1, 3 over 2, minus 1/2. And we can check. If I take minus 2, 1, 3 over 2 times minus 1/2, and I multiply that by the original 1, 2, 3, 4, what would I get? I would get minus 2 times 1 plus 3 times 1, minus 2 times 2 plus 4 times 1, 3 over 2 times 1 minus 3 times plus 3 times minus 1/2, and 3 over 2 times 2 plus 4 times minus 1/2. And this would be minus 2 plus 3, that's 1. Minus 4 plus 4, that's 0. 3 over 2 minus 3 over 2, that's 0. 2's here would cancel. And so I have plus 3 minus 2, 1. So that's our inverse. Another example. Use inverses to solve this system. X minus 2y plus 3z equals 1, 2x minus y minus z equals 0, and minus 3x plus y plus 4z equals 0. Same system that we had before where I was talking, we actually solved for the x value using Cramers rule. Now we want to solve for the entire system using inverses. So the idea is, if I think about this as ax equals b, I know according to Cramers' rule it has a unique solution. But let's actually find that. So this would mean that A is the matrix 1, minus 2, 3, 2, minus 1, minus 1, minus 3, 1, 4. And so now I want to find a inverse. And, geez, this is the last chapter. I went through these up. I have another one. And we're going to do the food network version. So you take this guy, 1 minus 2, 3, 2, minus 1, minus 1, minus 3, 1, 4, augment it with the 3 by 3 identity matrix, put it in the oven, and ding, this comes out. On the other side, you'll have this delicious meal that looks like minus 3/4, 11 over 4, 5 over 4, minus 5 over 4, 13 over 4, 7 over 4, minus 1 over 4, 5 over 4, and 3. Right, so you'll find the reducer echelon form. At some point, you're going to divide all the rows by 4. You're going to end up with something like that. So you find the reducer echelon form. So this would mean that A inverse equals this matrix. And that would mean that your X, the solution to this system, will be given by that whole matrix times the B vector, which is 1, 0, 0. And if you did that multiplication, put that in the oven. If you did that multiplication, you would get the answer which corresponds to what we got from Cramers. So this is would be a problem on the last test, right? I'm going to give you some system. I'm going to tell you, find the inverse of the coefficient matrix, and you're going to do this thing, or the second method I'm going to show you. You're going to get some answer, and then part B is going to say something like, use part A to find the solution to the system. In which case, you're going to take your answer from that part and actually just multiply it by this vector, and that would actually be the answer. And once
Professor, the x value would be negative 3 over 4 y.
Yes, the y would be minus 5 over 4 and the
Okay.
let me show you the other method. And which method you use to find the inverse, totally personal preference. I'm not going to favor one as opposed to the other. So if you happen to really like row reduction, you can do this all the time, and that's your thing. That's great. Just make sure you're good at row reduction. If you realize that finding the reducer echelon form is not your thing, you always add something incorrectly and something always goes wrong, you might want to try the other method, which is the adjoint method. So this method is strictly, it's based on a formula, and to actually find, I need to define some things in the formula. So let A n by n, let's say I can describe this as Aij. All right, so that's just, A11, A12, column 2, blah, blah, blah. The matrix its matrix of cofactors is the matrix C equals Cij, n by n, where Cij is the ijth cofactor. Right? Literally the same guy from the determinant. So it's the minors followed by the sign. The sign changed that from the checkerboard pattern. So the adjoint of the matrix A, this is called the adjoint of A, is equal to the transpose. So we define what transpose is. You're switching rows and columns of the matrix of cofactors. So you find all the minors, you create a matrix with the minors, and then you take the transpose of that matrix, you get what you call the adjoint matrix. And so now, here's the definition. Or the method, basically. The method comes to us in a single formula. Let A put n by n be a matrix with the determinant of A not equal to 0, then A inverse will be equal to this formula. 1 divided by the determinant of A times the adjoint of A. Example. Use the adjoint method to find the inverse of ABCD. First of all, the determinant of that guy is going to be what? AD minus BC, which I would assume is not 0. And now let's find the matrix of cofactors. So now remember, the matrix of cofactors takes on certain signs: plus here, minus here, plus here. And this is going to be the determinant of the guy you find by blocking out the A's row and the A's column. That's just going to be your D.
Professor, what, like, so determinant of A is
Yes,
AD,
block this out.
AD
So D is just the guy.
That's the
so
minors.
A,
That's the minor.
okay, okay.
Then you move into the position of B, block out everything in its row and its column. That's going to be the C.
C.
Move in the position of C,
C would be
block out everything in
B.
that row and that column. The determinant of that is B.
Okay.
And if you move on to D, block out everything in that row and that column. You get A.
A.
And so now the adjoint in this case, the adjoint of A will be equal to C transpose, which is going to be equal to, the first row is going to become, the first column. So I'm going to take the first row, now becomes the first column, so that's going to be a plus D minus C. And the second row is going to become the second column, so that's going to be a minus b plus a. Which means A inverse for the 2 by 2 is 1 over the determinant of A times this matrix. Or it's 1 over AD minus BC times D minus B minus C A. In other words, you want to find the determinant of a 2 by 2. Swap these two, take the negative of those two, and divide by the determinant. And it's easy to say that for a 2 by 2, so they just usually memorize this formula, but it came from this. And it turns out, though, that this works in general. It's just that if your A is a 3 by 3, the formula is not going to be that pretty, right? But the method is something that you can always use. So, for example, I can find the determinant of the other guy, the guy we already found. And we'll do the food network version again. So, A was the 1, minus 2, 3. B is the 2, minus 1, minus 1. C is the minus 3, 1, 4. And here's what you would do. First, find the determinant. That's actually going to be 4. Previously found. Then what you're going to do is you're going to find the adjoint of A. Now that's going to be some huge matrix transposed.
Wait, why is it
Now-
so big?
But I'm going to fill it in, and it's going to take some stress. Okay? What this means is you're going to find the matrix of cofactors, meaning each individual number, you're going to replace it with the cofactor of that position. So in the first position, there's going to be a plus sign, because that would take the cofactor. It is going to be the determinant of the matrix I get by blocking out that row and that column. Then a minus sign for the second position. So the 2, I'm going to replace it with its cofactor. So that's going to be 2 minus 1 minus 3, 4. So instead of doing row reduction, I'm literally just going to each position in the matrix and finding its cofactor. Then it's going to be a plus. Now I'm in the position of the 3. Block out its row and its column. 2 minus 1 minus 3, 1. Go down to the position of 2. Block out its row and its column. That's a minus. And you're going to have minus 2, 3, 1, 4. Plus. Move on to this guy. Block out his row, his column. That's going to be 1, 3, minus 3, 4. Move on to this guy, block out his row and his column. That's going to be a minus. And that's going to be 1 minus 2, minus 3, 1. Move down to this guy, plus, block out everyone in his row and his column. Minus 2, 3, minus 1, minus 1. Minus. Move on to this guy, block out everyone in his row and his column. 1, 3, 2, minus 1. And finally move to the 4. Block out everyone in that row and that column. You get 1 minus 2 and 2 minus 1. These you just do the cross multiplication, find all the numbers. When you do all of that, you take the transpose. And that's going to give you the adjoint, right? But I know there are some people who would rather do all these products as opposed to doing a row reduction for the 3 by 3, because that might take a lot of steps if you're not sure what you're doing. And so that would actually give you the adjoint. And so then basically the inverse is going to be 1 over 4 times the adjoint, which is going to be the matrix that we previously got. So that's going to be 1 over 4 times, when you do all this, you will get it to look like -3, 11, 5, -5, 13, 7, -1, 5. Alright, so this guy ended up being a -3, this guy ended up being a 5, this guy ended up being a -1, and so on and so forth. Yep, and that's it. So those are two ways to find the inverse, and once you find the inverse, you can actually solve the system, right? The inverse existing literally means the system has a unique solution. So we'll stop there, and on Tuesday, we'll talk about eigenvalues and eigenvectors, and I'll have an application of those.
Are they fun?
They're extremely fun. Eigenvalues and eigenvectors, it's going to be very cool.
Anything towards the end of the class is never fun.
No, it's going to be really fun. That's actually and the good thing is that questions involving eigenvalues and eigenvectors, they're always going to be of 2 by 2 matrices. They're never going to ask you anything bigger, so it's not like it's going to be like, oh my god. It's just going to be an interesting thing that you will only be required to do for a 2 by 2. So, it's going to be fun.